Okay, we will start. In our discussions last time, I told you that all our studies done in the last few weeks were to do with translational motions and dynamics, where forces and parameters like forces, we found out the resultants, we connected it with accelerations. We had parameters, physical quantities like velocities and displacements. This was our translational world. And we went about it in a certain order. First, we understood all physical quantities to do with motion, then what causes motions, forces, and then we developed certain tools from the Newton's laws, like work energy and impulse momentum, which helped us understand the dynamics involved in different situations. But if you had focused clearly, you would have found that most of the time, simple forces, finding out the net force and connecting it to acceleration, and then looking for works done by different forces and connecting it to energy, changes in energy. They were all focused on translational dynamics. For us to understand rotational dynamics, the easiest path is to draw analogies from whatever we've studied so that we can skip over certain academic exercises. We don't have to do them. Here, we connected the net force to the momentum and we said that the net force is nothing but if the net force is zero, then the momentum is conserved. We said something like that. That means P has to be a constant. That's why its derivative is zero. We had learned to Connect the net force to momentum, momentum changes, etc. And if you recollect, we said that if mass remains constant, we shifted the change to this. And we said mass remains constant. I was supposed to discuss certain situations where varying masses were involved. I have not done that. The rocket equations, etc., etc. I'll do that. In fact, we've hardly plunged ourselves into doing numericals in mechanics because I personally feel that we must have all the tools in our hands. Then let the dynamic situation involve translations, involve rotations, involve a mix of this. I should have my tools to break up the problem and analyze my dynamic situation. So for me to understand rotational dynamics, which is a little tedious, involves a lot of academic working. I don't do that to a great extent. Or even if I do that, I run through it very fast and I quickly draw analogies from here. Except in rotational dynamics, I use certain physical quantities like torque, like angular momentum, like angular acceleration, like angular velocity, like angular displacement. The relevant physical quantities I define, and then I draw analogies for relationships. If net force is connected with change in momentum, then net torque too is connected with change in angular momentum. If the net torque, if the net force is proportional to acceleration, proportional in magnitude, but in the same direction, then the net torque too will be proportional to angular acceleration. And the directions, once we have defined direction of vector physical quantities in rotational dynamics, which is quite different from the way we defined it here. We just drew an arrow and we said, that's it. It's a little different here. But once we understand that, and once we've defined these physical quantities, then we draw the same arrow. Because it is very difficult to picture torque or angular momentum. But it's easy to picture net force, push or pull, net, and momentum. So we understand the dynamics here, and then we try and predict what will happen there. Oh, there's a net force. Oh, there will be a change in momentum. Oh, there is a net torque. Oh, there will be an acceleration. Net torque, change in angular momentum. This is important for you to do. Otherwise, you will find the dynamic situations in rotational dynamics very tough. I spin a ball. See, rotation. It goes down and it touches. There's a sudden impulsive change in the spin. Oh, I go to this place and I say, impulse, momentum. There was a linear impulse, a force which acted in a short time. And that was connected to change in momentum. I spun a ball and it dropped on the ground. Sudden change in the rotational dynamics. Then there will be an angular impulse equal to change in angular momentum. See how easily I connect. Easy to visualize, easy to grasp, very difficult. And look at this. I did not put down any symbol for angular impulse because there isn't in physics. I had to write it in full words. What was impulse? Force, time. What is angular impulse? Torque, time. A rate of change of linear momentum with time gives you net force. A rate of change of angular momentum with time gives you net torque. If the net torque on a rigid body is zero, then there will not be a change in angular momentum. This will be a constant. But the definitions of torque and angular momentum are complex. There is a reference point involved. There is a reference point or an axis involved. And if you are finding out the talk about a reference point or an axis, you must see that the angular momentum also is found about the same reference point and axis. You have to be very alert. And so we will always write this, and so we will always write this, and so we will always write this. Otherwise, it is meaningless. Then does the work energy theorem, network equal to delta K, is it valid here? Why not? All the things that you learned in work energy are valid here. Net work done because of the net torques. Net torque. The only difference is linear kinetic energy, half mv squared. Angular kinetic, rotational. See, angular kinetic energy. We say rotational kinetic energy. Okay. We will soon realize also, while we are dealing with our problems, that translation and rotation keep happening together, interconnected. How? This is an extended body, a stool. It has a center of mass. If this stool were to go through a dynamic situation, somebody pushed it, push. Look at what happened. There was a translation, and if I were to draw an axis about this point, the center of mass, an axis about the center of mass, there was a rotation. There was a translation, there was a rotation. You watch me walk. No human being on earth walks straight, all right? Let's be clear. However hard you try. As we walk, we translate, and we also, if you notice, rotate about an axis through our center of mass. This is what Newton said is the dynamics I'm trying to discuss. That there is a translation plus rotation in all dynamic situations. The center of mass translated and then about its axis rotated, final result. So he says that translation plus rotation is what he calls rolling. We all roll in the physics sense. We translate and we keep rotating about our axis as we move. So, our problems, the final problems in rotational dynamics, when we come towards higher levels in another 2 lectures or 3, will be to do with rolling. The most difficult situations. Example, roll this ball. Center of mass, translate. It's got velocity, it's got acceleration. And it rotates about an axis through its center of mass. So, how do we look at it? We Shrink the entire mass of the ball to a point, understand the translation, and then we spread out the mass and make it into a ball and draw an axis and understand angular velocity, angular acceleration. Linear, linear. Both are happening. Translating, rotating. Rolling. Bring the mass to a point, spread it out. Spread of mass. Moment of inertia. See? It's so easy. A new physical quantity, Newton introduced moment of inertia. Spread of mass. You will understand the rotation. Bring it to a point, you will understand the translation. If you recollect, I told you that though I write dynamics of rigid bodies, I only took the mass, brought it to a point, drew a box around it, and I said, let's discuss the dynamics in a very limited way. That's why when I wrote the dynamics of rigid bodies, I got a phone call from one of my IIT students, says, sir, wrong. The dynamics of rigid bodies involves not only this, shrink, and this, but spread. You must make it clear to the student. So I made it clear to you last time that we do not look at the dimensions. We do not look at the spread of the mass for the time being. We will do that once we come to rotational dynamics. With the chapter of rotational dynamics done in the next few lectures, then I will have all the tools to discuss dynamics of rigid bodies. That's when I will come into action. That's when I will keep throwing assignments at you and discussing numericals. Now I'm comfortable. You have to get comfortable. And 35% of your syllabus will be able to pick problems, the best, toughest problems, and solve them. This is good. Spread of mass, moment of inertia. What a name. What a name. Our forefathers gave this name. I mean, it's weird. Moment of inertia. I don't know what it means. It's meaningless. They couldn't find a proper word. Symbol. This spread of mass, moment of inertia, will also be about an axis. About which axis are you spreading the mass? Are you spreading the mass about this axis? Or are you spreading the mass about this axis? Or are you spreading the mass about this axis, spread and spread? About which axis are you spreading the mass? You must mention. Moment of inertia about which axis? You know, I know. This disk, this sphere, this rod, This ring, disc, sphere, rod, this book or this sheet, they all have the same mass, which was not the problem when I was discussing translation. I just reduced everything to a point and I said, this kind of dynamics, it doesn't matter. The spread doesn't matter that time. But now it matters because rotation is involved. You know very well, a ring will rotate quite differently from a disc. A sphere will rotate quite differently from a rod, and the rod will rotate quite differently from a sheet. Though they have the same mass. If I were to take this and this and this and roll them down and incline, just release them. They have the same mass. According to my study here, they all should reach the bottom at the same time. But all three reach at different times. Though they have the same mass. Because the moment of inertia is different about an axis through the center of mass, if we consider. It's different. Here the mass is spread out here. Here the mass is spread out over this area. Here the mass is spread out over a volume. We will learn how to find moment of inertia. We will remember the moment of inertia is about the center of mass for certain standardized objects. The best thing about our 10+2 courses, I told you rotational dynamics is very difficult, but not for you. Because at 10+2, they have very few rigid bodies which will be discussed. The ring will be discussed, the cylinder will be discussed, the disc will be discussed, the sphere will be discussed, or a simple laminar sheet will be discussed. We will learn how to find out moment of inertias, about the center of mass, moment of inertias, about different axes. We will learn how to find them, we will remember them, so that we don't waste time in the exam looking for the moment of inertia, which will be required. Just like Newton's laws in translation, where the net force was proportional to acceleration, and when we removed the proportionality, we brought in mass. Newton, in rotational dynamics, when he connects the net torque to the acceleration, when he removes the proportionality, he brings in moment of inertia. So mass, when you draw an analogy, gets connected to moment of inertia. Force gets connected to torque. Linear momentum gets connected to angular momentum. Linear velocity, angular velocity. Linear acceleration, angular acceleration. Linear impulse, angular impulse. Now it's becoming easier to grasp. So you remember, we will be covering all these things. And next time when I ask you, you'll know that if these 3 rigid bodies or 4 rigid bodies were to be released on an inclined plane, then which one is going to reach first? Which one is going to reach last? You will know that. And you will enjoy the chapter if you keep your mind open. And instead of saying, oh, how tough, you say, how interesting. If I had an arrangement in a lab, and most of the things you can do at home, simple things. Oh, I could have seen the dynamic situation. It's pure magic. It's really pure magic. It's superb. Great. In our last class, we were talking about the relationship between the torques and the angular momentums. We took a simple example of a translational dynamic situation, and we said you can find torque, you can find angular momentum even for this dynamic situation, though there is no rotation. You just academically write down the definition and find out the value. Though you might not be able to use it effectively to explain the dynamic, because force and simple motion parameters were enough. You didn't have to go in for torques and angular momentum. But academically, the examiner can ask you, find out torque, find out angular momentum. Dynamic situation is the object was moving in a straight line. But we still found out because the examiner wanted us to. You remember that. Don't ever think that torques and angular momentums are only connected with rotational dynamics. They can be found only when rotation is there. No, they can be found out when translation is there, but they will not help you out. But they can be found out. Okay, that's what I was trying to tell you when we were doing that simple example. I'm going to take another example within the next 5-10 minutes. And that involves some element of rotation. And then you will probably respect torque and angular momentum and their mutual connectivity. And when I really shift into more complex situations where rotations are involved, you will understand the power of torque and angular momentum. These two physical quantities, you have to know them very well, right from definition to how to find them. And I will always keep talking about it and pushing you towards that. Rather than studying rotation the way you've been doing it in school. Before I take up that example where a little bit of rotation is involved, and I talk about torques and angular momentum and their connectivity, before I do that, since I was trying to tell you that the study of translational dynamics done in the previous couple of months, we can draw a lot of inspiration from them, analogies, and predict a lot of things in rotational dynamics. Fair enough. You remember when we did translational motions or dynamics, I said, let us study straight line motions. And subsequently, we went into the Newton's laws and studied the dynamics, forces to do with straight line motions. Straight line motions. Our sir called it 1D. Pathetic. Anyway, straight line motions. And then we said 2D motions. Motions in a plane. There was more flexibility now. And once motion in a plane came into the picture, our straight line motion could be taken and curvatures could be projectile motion, circular motions, etc. And then 3D, of course, extending it in space. Bizarre motions. In rotational dynamics, too. What was this? Straight line motion. Object traveling in one straight line along an axis. The elephant was restricted to walk along the x-axis. Restrict straight line motions. Could be this way, could be on an inclined plane, but straight line. Could be in the vertical plane, straight line. Straight line. One axis. One axis. Restricted. 1D motion. Fixed axis condition. Fixed. You have to travel along this. Fixed axis condition, rotational dynamics. The disk has to rotate about this axis. Fixed axis condition. The stool has to rotate about this axis. The stool has to rotate about this axis. Fixed axis condition. The rod has to rotate about this axis. Fixed axis condition. Analogous to 1D. Crazy. Think about it. Fixed axis condition. Fixed axis condition. Fixed axis condition. Fixed axis condition. Analogous. In what sense analogous? analogous to mass, moment of inertia, analogous to this, analogous to this, net torque. Kinetic energy, fixed axis conditions. Moving along this, kinetic energy at any instant. Translational or rotational kinetic energy, fixed axis condition, half m I omega I about x. Analogous. So simple. Fixed axis. Just direct analogies. Work. F dot ds. Work. Force, torque, linear displacement, angular displacement, dot dot. Unit, joules, 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 joules. Torque, about some axis, fixed axis condition. Talk about axis. Work done. In going from theta 1 to theta 2, angular displacement. Work done in going from S1 to S2. Displacement, linear. Fixed axis conditions, direct analogies. You name it. Linear momentum. Analogy. Angular momentum about an axis. I about an axis, omega. You put an arrow here, you put an arrow here. I am avoiding arrows. When we were in 1D, we avoided. We said we know the directions plus and minus enough. We know the directions plus and minus enough. Clockwise, anti-clockwise, about a fixed axis. Clockwise, anti-clockwise. One is plus, one is minus, whichever one you want. But look at the analogy. Mass connected to this. Linear velocity connected to angular velocity. Linear momentum, angular momentum. In 1D, you can avoid this because the plus and the minus were enough to tell you the direction. In a rotation, we normally avoid this. I'll tell you why. But if you put it, you've done nothing wrong. If you do it, nothing wrong because it's a fixed axis condition. Every particle of the disk has to rotate about this axis. No problems. Wow. See the connectivity. See how easy life can become. Yes, network is equal to delta K. Yes, why not? Except rotational, except network will be found this way. Net torque dot d theta. Delta KR. Fixed axis. Omega final square minus omega initial square. So, when we study, we are just starting our studies. We are just trying to grasp. I'm just giving you a bird's eye view into rotational dynamics. You will have fixed axis conditions, where we call it pure rotation conditions, where the rigid body is rotating about an axis, pure rotation. And we will have translation plus rotation, which we will call our rolling. Pure rotation, and then translation plus rotation, rolling. You will have rolling with slipping, and you'll have rolling, pure rolling. No slipping, no sliding. You know very well, if you spin a ball and just roll it, it's going to slip. And after some time only, it will pure roll. In our 10+2 study, this is not there. Though I will take one or two examples to explain. Only pure rolling is there. So when I say rotational dynamics at 10+2, pure rotation, pure rolling, with no slip. Rolling, translation plus rotation. 85% of the problems in the exam in mechanics are in pure rolling. There is an often mistake made by your sirs. They say in translation we had sliding friction, and here we have rolling friction or rotational friction or something like that. They are wrong. They are totally wrong. Rolling friction is a total different concept, and it is not there in 10+2. And I will explain you that. The same friction we studied here, sliding friction, is the same sliding friction here. Just because I say linear velocity, angular velocity, linear acceleration, angular acceleration, linear momentum, angular, then you might have the tendency to say linear sliding friction or rotational or rolling friction. Wrong, 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 wrong. Your sirs are wrong. And they do that. They do that. And some of these guys call themselves to be IIT graduates. Impossible. Somebody who gets through IIT, advanced exam, JEE advanced, will never make this stupid error. So you don't ever say rolling friction. My students, no. And if somebody says that, you correct him. You say, hey, Babu, what is rolling friction? What rubbish are you talking? Ask him to explain you rolling friction. He won't be able to explain. I will explain you rolling friction, which is not there in your curriculum. And in most of the dynamic situations, it is the sliding friction which is so huge and dominating, and the rolling friction is so small that it is neglected and it is never taken in the problems that we do at 10+2. And the whole concept is different. But I will explain you that after 2 or 3 classes. So we are clear that when we study rotational dynamics, we'll have fixed axis conditions, which is analogous to my 1D. And we will be studying translation, rotation, that's rolling, pure rolling. No sliding. That's our course. Get this clear. You must know your limitations. You must know where you are heading. Don't just plunge into something without having an overall bird's eye view of the entire chart. So that's where we will be heading. Finally, rolling, pure rolling, we'll be taking up problems which involve rolling, collisions, explosions, everything in rotational dynamics, just like we did in translation. Remember, we have done nothing as far as numericals goes. Another 5 lectures and we'll be plunging ourselves into numericals. Collisions on billiard tables and work energy concepts and vertical circular motions and all those things that we studied. I'll be throwing problems at you to see how flexible your mind is in catching and applying the concepts. That's the only way you can study mechanics. Okay. So, we continue with our discussion where I told you that we must build up our understanding of these 2 physical quantities, talk about the reference point and angular momentum about the reference point. First, understanding the definitions, then the relationships between the 2, how they're connected, how the dynamics brings them together. That's paramount, very important. I told you that I go about understanding rotational dynamics this way rather than the conventional way in which it is done in your institutions or schools, is because through sheer experience, I found this is the best way to handle this chapter. If you really want to solve problems, if you just want to chronological order in which finish the syllabus and be content that syllabus is over, then you will not understand rotational dynamics. You will just do it as an academic exercise. Find out moment of inertias, find out this, find out that. I want to create a situation such that you will not only teach your friends, but when I throw a ball and there is a collision and there is a spin and there is a collision and there is rotational dynamics, you should be able to analyze it with great confidence. That's what I'm interested in. So we wrote down the definitions, if you recollect. We started with L and we said that the definition is very, very elaborate, and whoever thought of it must be crazy. But as we get into rotational dynamics, you'll realize how powerful these definitions of torque and angular momentum were, and how easy they make life for you when it comes to understanding dynamic situations in rotation. But right now, they look crazy. So the definition of angular momentum was given as a cross product units, meters, mass, kilograms, meter, velocity, meter per second. Kilogram meter square per second. That's all. I mean, nothing great about the units. But look at the complexity of the definition compared to linear momentum. The vector P is in the same direction as V and multiplied by a scalar. So it was easy for us to perceive that P vector is just in the direction of V. So easy to represent the linear momentum. But look at this. This is crazy. This mathematical expression tells me that L, angular momentum about a reference point, is a vector perpendicular to the plane formed by R vector and P vector, or R vector and V vector. Plane perpendicular. Let us see. Some reference point from where I'm applying the definition. And I told you, the best thing about this definition is you can select the reference point. You'll see that in problems. When I do problems in fixed axis conditions, in rolling, etc., I will tell you, can we choose this or should we choose this? And soon you'll become an expert at selecting the correct reference point to simplify the calculations. From the reference point, the position of the object is R. See? And P, the linear moment, M into V. R cross V or R cross B. If this is in this plane, then R cross V. There. Can I show it like this? Yes, not bad. If this is in this plane, then this is okay. Perpendicular to the plane formed by R and V, this plane, or V cross. Good. I did R cross V here, but I brought it here to the reference point. L about O. This dynamic situation was the rigid body was moving in a straight line, 1D motion. But I still managed to find L. And what was the magnitude? R perpendicular MV. Magnitude. R perpendicular from the line of action. Line of action. From the line of action. Draw a perpendicular to the line of action. R perpendicular. Let us say it was D. At this instant, at an instant, the V could be changing. At an instant. Angular momentum about mole at this instant. Examiners given. There. Value, answer. Kilogram a meter square per second. Magnitude. Direction. But found it for a simple linear motion. Angular momentum. But I'm not getting anything much out of it. Yes, you will not. Because this guy becomes more powerful and meaningful when rotations are involved. Otherwise, academically, you can find out, and I found out the value for this particular dynamic situation by taking a reference point and I wrote it. You remember this, you can find it. An examiner will ask you to find it for a dynamic situation where there is no rotation. You better find it. And don't say not possible like a donkey. Good. If I would have drawn forces, then N balances FG. There is no dynamic in this situation. Dynamics is only in this situation. Friction is involved. According to my experience, I know that if friction is in this direction, motion is in this body will slow down. I know that. Let us find out torque. Definition. If you have found out L about O, and if you want a relationship between L and torque, you better find out torque about O. Common sense. Same reference you have to use. You can't use different reference for this and different and try and find out a relationship. You won't get it. But you will make this mistake. You will see that in rolling, you will make the mistake. You found out torque from some other axis and you found out angular momentum from some other axis. And then you were trying to connect and you went wrong in the problem. So you'll have to be alert. Let us find out the torque about O. Applying the definition. The definition is very, very elaborate. Torque net in the direction of the dynamics is equal to R cross F net in the direction of dynamics. That's equal to R cross F in the direction of the dynamics. There is only one force, which is the net force, which is friction. R cross F. R cross F. If this is in this plane, R cross F means down. Yes. It has to be in the opposite direction of the motion vector. Motion vector. Motion vector. If the motion has to slow down, then we know that the momentum is in this direction and the acceleration is in this direction because of this, and hence it will slow down. Acceleration, velocity, opposite direction, slow down, brakes. Then if this dynamic, the body is going to slow down, even though I'm finding out this very complex physical quantities which are very, very powerful in rotational dynamics, but they do apply for this situation. When I find out angular momentum and torque, I find that the motion vector is this way and the torque is this way. Brakes, opposite. It will slow down. But it is very stupid that I'm trying to explain this dynamics using rotational parameters, though academically valid, but they are just complicating my life. R torque in magnitude net is equal to R perpendicular, which is equal to F kinetic, F kinetic, F kinetic. That's equal to R perpendicular, line of action, and from the reference point, perpendicular direction, D, F, K. And Fk you can write later on is nothing but mu k into n, etc. Put it there and put the value of n equal to mg, all that you can do. You can do. No problems. But my purpose is to try and get a connectivity, though mildly there, for a dynamic situation which is a 1D straight line motion, though relationship can be there, it is a mild reflection. But let us take an example where they now show us some kind of a more powerful interaction. We can find out torques because of different forces, but I'm taking net torque just to connect the momentum of the rigid body. You can't connect it to torque because of different forces. Torque because of net force is connected to this. Net force is change in momentum connected. Net torque. That's how I'm taking it. Definition. Yes, this can be written as Newton's laws. This can be written as no problems. But did you realize how the linear fellows through an arm, position arm, connected to angular fellows. Linear forces, how connected through arm are you getting? There's some kind of a connectivity. Who, the guy who made the definitions has given. I'm taking what is known as a example of a conical pendulum. Pendulum everybody knows. Okay, simple pendulum everybody knows. Is Sampath there?
Yes, sir.
Ah, Sampath. Sampath, what's a simple pendulum? I mean, when I tell you, don't give me some kind of a definition like a donkey that you give to your teacher. Just tell me what is it?
Sir, which oscillates. Sir,
Bloody hell, this rod is also oscillating here. Is that a simple pendulum?
no, sir.
Then
So to a string, to the end of it, a ball is attached. If like it is attached, if it oscillates and it makes an angle less than 90, then it can be treated as simple pendulum.
even for this rod,
No, sir.
then how did you pass 10th? Sampath, you cheated or?
No, sir.
You can somebody like Sajiv is there? Sajiv? Sajiv, are you there? I can find out.
Yes, sir, I'm there.
Good. What's a simple pendulum, Sajiv? Sampath doesn't know.
A bob attached to a string which is suspended on a fixed point and it oscillates.
So, Mr. Sajiv, another fellow who has passed his 10th class at flying colors, says it is a string with a bob fixed. Is that so? Which oscillates? Does it have to oscillate to be called a simple pendulum? Or just a simple string with a bob hanging on it is a simple pendulum, Mr. Sajiv? Sajiv,
Sir,
a string with a bob hanging, is it a simple pendulum? Or does it have to oscillate to become a simple pendulum?
it is a simple pendulum.
It is a simple. Anybody wants to improve Sajiv's definition because it is not correct, Hitesh? And of course, inextensible. In real life, you can never have a simple pendulum. When your school teacher told you, let us make a simple pendulum and let us find out the time period of a simple pendulum, she was not correct. Because any string you buy from the market or a shop or whatever is going to have a mass. Also, the bob is going to have a dimension, whereas in a simple pendulum, the bob doesn't have a dimension. It is just a point which has a mass m. It's a very theoretical concept. Massless string of, let us say, length L and the bob having a mass m, which has no dimensions. Imagine. That's a simple pendulum. Please don't forget this. And when you wrote the time period of a simple pendulum, if you would have, for your pendulum, found out the time period with the formulas given by your teacher, t equal to 2 pi root of L by G. I think your teacher gave you some formula like this. I think it was something like this. Where G was the gravitational acceleration in that area where you have set up your simple pendulum. Then had you constructed a simple pendulum using a real string and using a bob which had some radius, some ball, and you would have found out the time period by counting, how did we do it? We just held the bob towards us and we released it. So it went, it came back. We said 1 cycle completed, 2, 3, 4, 5. So when it goes this way and it comes back, the time that lapsed is called a time period. So what we did was we just counted 1, 2, 3, 4, 5, 6, 10, and we measured 5 minutes. Then we took 5 minutes, multiplied it by 60, divided by 10, we got the time period. Then, after getting the time period, by actually carrying out the experiment, had you done 2 pi or root of, measured the length and found out the G in that location and calculated it, you would find this quantity is not equal to this. Because this formula was for a simple pendulum, whereas you had not constructed a simple pendulum. Your string was having a mass, your bob was having a dimension. Another thing also, the pendulum, when you pull it, you have an angular amplitude and then you release it. This angle is supposed to be so small that sine of the angle of theta is equal to theta. That's only for 1 degree or 2 degrees. You can look up the table. Find the value of 2 degrees in radians by multiplying 2 into 2 pi upon 360. Find out the radians and find out sine 2 degrees. You'll be surprised, the values are almost the same, left and right. But that is for 1 degree, 2 degrees. But when you pull the pendulum towards you, you might pull it by 15, 20 degrees. You can't pull it by 1 or 2 degrees. And if you pull it by 1 or 2 degrees, you won't be able to even count the oscillations. This formula given to you by the teacher was a terrific approximation. First of all, you could make a simple pendulum. Secondly, the formula itself had such approximations where you said the angular amplitude has to be within 1 or 2 degrees. Just too much. But when you got the answer incorrect, you guys better become alert, you guys better understand that this is not just a storybook. Every word, every vocabulary word is going to have a meaning. Okay, let me not digress into this because simple pendulums, and let me tell you something. The pendulum that you made in your lab is not called a simple pendulum, it's called a physical pendulum. It's called a physical pendulum. Anything which deviates from a simple pendulum is a physical pendulum. Your grandpa's clock, which has that big pendulum, is a physical pendulum. A simple stick is a physical pendulum because it has a mass distribution. Physical. All pendulums in real life are physical pendulums. Theoretical pendulum, which you constructed, was a theoretical pendulum, simple pendulum, to study oscillations. We will study oscillations because of simple, then we will shift them into physical pendulums, and we will do that when we come to the last chapter of mechanics, which is vibrations and oscillations. That time I will discuss with you all this again and again. So, when you take a simple pendulum and you do what I am doing now, it becomes a conical pendulum. The simple pendulum, is rotated in such a way about this axis that it traces out a perfect circle with a radius r. So this circle has a radius r. And the string of the simple pendulum generates a cone. And a conical pendulum, when I say, will have a fixed angle of the cone, that half an angle should. Theta naught. That's conical pendulum. Simple pendulum generating a cone where the bob traces out a perfect circle R. And if I say this is constant, then at any instant for this bob, the linear speed is constant as it goes. If this is constant. So I have drawn a conical pendulum, which is a simple pendulum, which is made to trace a cone with a fixed angle theta naught, measured from the central axis. It has a linear constant speed and an angular speed which is constant. I'm taking this example, and I told you last time that I'd taken this example, and to my surprise, This was 4 or 5 years back. They gave it in the IIT and discussed a big problem of almost 10, 12 marks based on this. And my students were very happy. They gave it in the advanced exam. So I am trying to connect the physical quantity torque with L. To be more precise, net torque with L. I'm trying to connect. My first example was simple linear motion. Now it's this, where I have brought in some kind of a rotational dynamics, mild one. Let us take two reference points. One is the center of the circle, O. And the other one is about the central axis, A. Let us find out L and talk about O and about A. Let us find out first the motion vector, L about O. Definition is R cross MB. Line of action is this. R is from the reference point position. R cross V. R cross V. Come back to O, draw it. Wherever the particle is, R cross V. Though this vector R is different from this vector, this is R dash because now it's changed. So R cross V. Same. Let us find out the magnitude. So the magnitude is equal to R perpendicular, radius, M into V. Wherever the particle is, wherever the bob is rotating about this, L about O is constant in magnitude because V is constant, R radius is constant, mass is constant, and it is constant in direction. It's uniform. Momentum, constant in direction and constant. Linear momentum constant. That means a dP by dt, which is equal to the net force, will be 0. That means the net torque about O should be 0 because that is equal to dLO by dt. But this is constant. Derivative of a constant is 0. So if we find out the torque about O, we should get a 0. Wow. Let us find out the torque. Torque. Definition. Always in the exam, put down definitions. Net force. So now we have to draw the free body diagram because forces are unknown. Let us take any position which is convenient. All right, this looks more convenient. mg, tension in the string, dot, 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 resolve this, you get T cos theta naught, this is theta naught. And this is T sine, the other component is T sine theta. R cross F net. So this gets balanced by this. T cos theta naught is balanced by mg because the pendulum is not going up and down. It's only going this way. And T sine theta is unbalanced, hence the net force is T sine theta. And the net torque in magnitude is equal to T sine theta in whatever direction is there cross R. T sine theta and R is this way and T sine theta is this way. And R is this way and T sine theta is this way. Cross product 0. Sine 180, 0. As predicted. What is the message? What is the message? The message is that if you are able to go to the correct reference point where the net torques are 0, then you can conserve angular momentum about that. Then LOI will be equal to LOF. Whether the particle is ya or ya or ya or ya or ya. Angular momentum is conserved about the reference point O. So in your problems in the exam, with experience and a little bit of practice, you will be able to find out the correct reference point. If you take it there, the torques are 0 and hence I will conserve angular momentum there, and maybe that will help me find some unknown parameters in the dynamic situation. Try and respect and appreciate what I'm trying to say. It is a very, very powerful definition for the net torques, for the torques and the angular momentums. The guy who thought of the definition was a genius. A dynamic situation, which is not a very difficult thing to analyze, but I am trying to stress the relationship, mutual relationship between torques and L's, between these two vectors. And I'm all the time drawing inspiration from my translational fellows. Linear momentum constant. Oh, net force should be 0. Reflected yaw. Angular momentum constant. Net torque has to be 0. Let's find out. And we get it 0. So in future, if you get for different positions of the object, L coming out to be constant in magnitude and direction, you can say that the net torque about that reference point is 0. And you might get some parameters, unknown parameters, which are required by the examiner. Great. Super. Very good. But let's see what happens when I take the reference point A. Instead of O, let me take A. Please bear with me. I know it's already 7:45 past. Just bear with me for 5-10 minutes. Just 5-10 minutes. So that I don't have to repeat this whole problem again. Now I'm discussing at the point A. All right, I've done it for O. Now I'm moving to A. Same dynamics, the same situation, the same conical pendulum. But this time instead of taking the reference point O, I am going to A. I am taking this as a reference and then looking at my dynamic situation. Can I extract something interesting? Let us see. Just give me another 5-10 minutes, please. Just 5-10 minutes. Let us take this position. Now I'm not taking this as the reference, this is the reference. L about A. I wrote down the definition. R cross MV. R is the position from the reference point to the line of action. From the reference point to the line of action. From the reference point A, which is to this. From A to this. From A to this. R. That slant is the R. This slant arm is the R. And M with the V. The V is this. So it's R, V. R cross V. This way. Perpendicular to the plane formed by R and V. Perpendicular to the plane formed by R and V. This plane, sloping plane. R cross V, sloping plane. But we don't show it here. We show it here. Let's write down the magnitude quickly. R perpendicular V. R perpendicular to V. This R on a cone, this slanting line will always be perpendicular to V. So what is this? L. L and V. Is it constant? Sampath, is the angular momentum at A constant? L is constant, M is constant, V is constant. Sampath, is it constant?
Yes, sir.
Sajiv, is it constant?
Yes, sir.
Oh my God. Sanjana, is it constant?
I guess, yeah.
No, it's not constant. The magnitude is constant, but not the direction. In this position, it is here. When it is in this position, again I will do R cross V. It will be like this in some other direction. And it will be in some other direction. And some other direction. And some other direction. Are you understanding?
Yes, sir.
So it's not a constant. So as this moves, this vector seems to be moving with the object and generating a little cone there. You notice? As the object moves, so does the L move. It is constant in magnitude. It is executing rotation. When does L execute rotation, the vector? When does the P vector execute rotation? When does it execute rotation? When the net force on it acts perpendicular to P. I told you last time. And if it continues to act perpendicular, the P vector will execute a rotation. And we say the object moves in a circle. You remember? But we never talked about this. We did this, we did this, we did this, and we said perpendicular force, hence this, and then we did again this, and we did this, and we kept showing V and V and V and V and V and V and V. And we said a uniform motion is executed. When the net force was perpendicular to the motion vector, when the torque will be about a perpendicular to the L vector will execute a circular motion. Wow. When we took it here, we got some parameters. When we shifted it here, something new is coming out. For the same dynamic situation, some more information I'm able to extract. Let me find out the torque and see whether the torque is perpendicular to this. What is the definition of torque? So I'm finding out the torque about A. So the torque about A is equal to R cross a net force, net torque. I'm only interested in the net. R net, first free body diagram. So let us draw the free body diagram. Mg tension. Whenever a force is going through the point where we want to find torque, then according to the definition, R cross force will be 0. So, because of this force, the torque will be 0. There is only because of this force. line of action of the force into perpendicular distance from the reference point, this, which is equal to R. And hence the torque, as per the definition, let us write down the magnitude first. Then the magnitude, net torque, since the only force left is this, and hence this becomes the net force, because this one, when it is going through the point through which we are finding out the torque, that means it will become zero. Then the only fellow left is this, and hence that's the net force. And the magnitude is given by m, g, and r. Perpendicular is r. What about the direction? R cross F net mg. R cross mg. There. How was this? This way. There. Perpendicular. Perpendicular. About. For every position, I do R cross F, perpendicular, 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 perpendicular. And hence, because the torque is acting perpendicular to L, L will rotate in uniform circular motion. Its magnitude, the motion vector's magnitude will not change. The magnitude will not change, but the direction will change. The L vector executes the motion vector L. When I take the reference, it executes a uniform circular motion. You remember when I told you about that toy where the torque was acting perpendicular to L, or your fan, your pedestal fan, when the torque acts perpendicular to the motion vector, the fan swivels. If it was allowed to move, it would have executed a perfect circular motion. Who? The L vector. And in turn, obviously, the rigid body. The rigid body executes a perfect circular motion. Motion vector. Torque. Now, I'm going to highlight this further in the next class. But try and understand what I'm trying to tell you. I am not concluding my chapter. I'm just trying to tell you that there is a mutual relationship between torques and angular momentum, between torques and the motion vector. There is a mutual relationship, and if you can exploit that mutual relationship, you will understand the dynamics involved in rotation very well. Whether it's a ball rolling, it's a disc rolling, or it's a rod which is tossed, which is rotating, you will understand. If you understand the relationship between these two, that they can give me an idea about the dynamics, then you will be able to analyze and give the examiner's answers. It's a super thing. It's a fantastic chapter. Please don't miss classes. Please attend, and please be alert, and please practice whatever I teach you. Even if it is not much, practice it when there is no class. There's nothing else I can tell you beyond this.